Hi, my name is Mariam. I am account manager at SELTECH. It's nice to see so many of you joining our SELTECH Sensors Converge virtual event. It's time to start our webinar. Julio, what's the plan for today?
Hi, Mariam. Hi, everyone. Today, we will have our partners and friends from AZOTEQ. During this webinar, we will introduce you to the new ways in which capacitive, inductive, and Hall effect sensing can be used to design unique user interface for kitchen appliance, home entertainment, and security systems. By presenting some current solutions, we invite you to get creative by identifying new technology possibilities. We love making your wildest tech ideas a reality. We will leave Paris to join the wonderful city of Cape Town, where AZOTEQ is based. So take enough cup of coffee, some water, and relax, not too much, and enjoy this webinar and stay safe. So, hi Jean, thanks for taking the time to share your knowledge with us. The platform is yours. Bye.
Julio, Mariam, thank you for the introduction. Yeah, it's indeed a pleasure to join everyone today from the wonderful city of Cape Town. We are fortunate that we are heading into our spring season. Julio, you guys are still, I still get some audio from the Paris office. If you guys can just mute. And then Savannah, if you can just give me a thumbs up maybe on WhatsApp to make sure that the audio and the video is fine, then I can get going. All right, ladies and gentlemen, thank you once again for taking the time to join us today. Savannah, is the screen, am I also on the full screen? If I can just get a confirmation of that. Just a quick introduction about AZOTEQ, maybe a quick introduction about SELTECH and our collaboration. AZOTEQ is a fabless IC design company headquartered in South Africa. We are operating from a beautiful location just outside of the city of Cape Town, where the AZOTEQ headquarters are situated, and also all the R&D activity. AZOTEQ is a fabless semiconductor design house. The company has been in operation for a good 22 years. We are not as big as many of the famous brands, but our size means we are agile and we can be very innovative. It is actually a very important part of our company culture to drive innovation, to be first with new ways to solve existing solutions. AZOTEQ have partnered with SELTECH for a good 8 years already. So SELTECH serves the sales activity as well as the fulfillment activity on the distribution side. SELTECH has offices in the US, Europe, and a well-established network in Asia. This means you have sales and commercial support in your region and in your time zone. But in the instances where manufacturing is done in Asia, SELTECH also provides that bridge between the European, or let's say Western world designing activity with the manufacturing and fulfillment activity to the contract manufacturers. Right. So for today, let me just make sure I'm on the correct screen. So for today, some ideas to open your mind on novel ways to implement user interfaces in not only appliances, but as Julio has mentioned, security systems or home entertainment systems. Really today, the purpose is just to share ideas and open your mind what can be done with AZOTEQ's technology in terms of the user interface. I just want to make a disclaimer at this point. We did not harm any animals in the making of this presentation. All right, let's get started. As I said, AZOTEQ has been in operation for over 2 decades. We are here to help you and to implement something new, and together we want to do something novel, something new, and something innovative along with you. The AZOTEQ portfolio started off as a purely capacitive sensing portfolio, anything from a single channel all the way up to 150 channels of capacitive touch sensing. Today, the sensor offering has been expanded to not only do capacitive sensing, but also including inductive and Hall effect sensing. Everything can be done in a single IC. And as we go through the presentation today, you will see the distinct advantages that this holds when you can build different technologies in different sensing technologies into a single chip solution. So I think the first and foremost, and maybe one of the most obvious solutions for home appliances or home goods would be a touch interface. AZOTEQ has a portfolio of sensors that can do anything from a single channel all the way up to 72 touch buttons. Now, in the instance of an appliance like a microwave oven, you will use this capacitive sensing buttons to implement your keypad and any other controls on the microwave oven. AZOTEQ's IC also supports gestures. So let's say you would like to perform some kind of unlocking function or a child lock. You can overlay a gesture function over the touch keys. So for example, only the adults can unlock the microwave oven's keypad, but a child that does not know the sequence cannot unlock it. The same if you want to embed a second user interface on top of the buttons. For instance, you may use the bottom row of buttons. If you just want to extend the cooking time for a quick 10 seconds or a quick 30 seconds, you can implement that with a quick swipe. I think it's a frequently used function on a microwave oven that you just want to extend for a few seconds or a fixed amount of seconds. And then a gesture can be a very nice way to very quickly, without needing to find the specific button that says additional 10 seconds, you can do a quick swipe to the right or a quick swipe to the left to perform a frequently used function. I mentioned earlier that our devices also supports inductive and Hall effect sensing. So let's say you have selected the sensor IC from AZOTEQ to perform the capacitive sensing on your keypad. You can repurpose one or two of the channels on the IC and dedicate them as an inductive sensing channel. Now with the inductive sensing, you can, for example, detect the fact that the door may be open or closed. So no additional components or no additional cost is required. The IC automatically supports multiple channels, and you dedicate one or two of these specific channels for the door open and close detection. So a nice way to reduce your BOM cost and reduce some complexity in your system. With the capacitive sensing comes the ability to detect a short-range proximity. Now, proximity sensing is performed in a very sensitive area of the capacitive sensing spectrum. We do not recommend proximity sensing for a critical function. We will never recommend it to turn your appliance on or off, for example, purely because of the sensitive nature of the proximity sensing. But it is a function that comes for free, and I will explain in a second what that means. And it can be used in a very convenient fashion. The fact that you already have capacitive sensing channels doing the detection of the key presses means you can either use the key itself and set up a very sensitive proximity threshold, or otherwise, as we have in the example on the screen, You can put a dedicated capacitive sensing electrode around the bezel or around the user interface area of your appliance. Now, as the user approaches, we will detect that small change in capacitance, and you can use that function to trigger something like backlighting or wake your MCU from sleep, that you get a much quicker response, or maybe you need to establish RF communication, something like that. So the proximity sensing, very suitable for a convenience function that is not critical to the actual operation of the device. I can just imagine in my own home that once you are looking to find the user interface, whether it be on your light switch or on your stove or any other kind of appliance, it's very nice for the user interface to light up as you reach out. If you think about home entertainment equipment that is often positioned just underneath your television set, you don't want all these bright lights that is illuminated all the time when you are watching your movie in a dark room. But you do want to find the touch key or the volume knob as you reach out to it in the dark. So a very nice, convenient feature that the capacitive sensing offers. I said earlier that the function comes for free. That is true because take the example on the screen where you have two touch buttons. You can select a touch IC with 3 channels from AZOTEQ. Use 2 of the channels for the touch sensing and dedicate the 3rd channel, can be dedicated to the proximity sensing. Another popular user interface would be a scroll wheel. Scroll wheels are designed using a minimum of 3 capacitive channels. These 3 capacitive channels are interweaved with each other, and as the user slides his finger, the effect of the finger would be dominant on the first slider, and as you move it to the second slider, this dominant weight shifts to the second slider. We interpret that position of the finger. So it can either be a wheel, or if you break the wheel open, it is a linear slider. Sliders and wheels, very nice user interface to navigate through various menu items. If you have 5 or 6 or 10 menu items underneath each other, the wheel becomes a very nice way to navigate such a menu structure. Of course, I assume my audience already realized that the fact of using touch sensing means you can have a completely flat and completely seamless outer shell or outer design. The example that we have on the screen here, if we combine that with proximity sensing, you can have a hidden until lit display. It means everything is dark. As we approach the user interface, we use the proximity detection to illuminate the controls as well as the display. You activate your controls, and then as soon as you remove your hand after a set time, 2 or 3 seconds, we can dim the display, and the whole button user interface display area disappears into the dark once again, and you have a smooth and flat finish on the outside. All right. So my first 3 topics was very much user interfaces that we have accustomed to and have become familiar to. The rest of the presentation, I hope I can open your mind a little bit about novel ways to use existing as well as new technologies. The first one would be what we call a swipe interface. The swipe interface is in essence a slider, but because it relies on the premise that you need to perform a very specific interaction in a very specific time, means that we are able to make a waterproof user interface that cannot be easily triggered by water. Capacitive sensing on its own is not natively immune against water interference. So AZOTEC have developed as well as patented technologies where we use up to 3 channels as a slider or as a swipe. We are looking for a very specific pattern in the swipe. This is controlled and configured on chip. How far should the user swipe and what should be the specific speed at which the user swipe. And only once a valid swipe is detected will we actually activate the function. Random water that comes onto the capacitive user interface will not meet these specific requirements. And that gives us a very high level of immunity against water interference. Water interference is something that is a practical challenge in all kitchen appliances. You want something with a seamless outer shell. We do not want apertures or membrane switches and the likes. Those have inherent reliability issues, especially as they age. It has challenges to put your appliance in the dishwasher, and of course, manufacturing challenges as well as additional cost. So the capacitive user interface allows you to have a very smooth outer shell, simplifying the mechanical construction and inherently gives you higher reliability since we do not have any effect on the user interface or the switches that are age related. Something interesting and relevant for kitchen appliances is grip detection. Grip detection can be done by capacitive capacitive touch sensing. The example on the screen, you would have a capacitive sensing channel either under the forefingers or under the thumb, depending on how the user would grip the appliance. It can either be used as a convenient feature in the case of the hairdryer. So the typical use of a hairdryer is to blow your hair a little bit, put it down, pick it up again, put it down, pick it up. And every time you release the grip, you can turn off the hairdryer as a convenience feature. It can also be used as some kind of interlocking mechanism where you want to make sure at least 2 interactions are activated. So it is not an accidental press of the power on button. You want to make sure the user is properly gripping the appliance and then activating a second switch. So in grip detection, either a very convenient feature, or secondly, it can be used as some kind of interlocking. It can even be set up such that you can avoid that a child's hand activates the interlocking mechanism and it only relies on an adult hand that is gripping the appliance. Coffee machines have inherent challenges with there's always some coffee dust and some ground coffee that falls into all the nooks and crevices of the coffee machine. Coffee machine have various interlocking mechanisms that need to detect it. The device should not operate if all the doors and all the shutters are not properly closed. The same goes for the tray detection. You need to detect whether the drip tray is in position or not. For such an appliance, we can either use Hall effect sensing or we can use inductive sensing to detect whether lids are closed, cartridges are in position, the drip tray is in position or not. Let me just say a few words on the difference between Hall effect sensing and inductive sensing. A little bit later, I will have more detailed graphics, how inductive sensors are practically implemented in an appliance. But for the moment, on a high level, we can just remember Hall effect sensing. We are sensing the disturbance of a magnetic field, or we're actually generating a certain magnetic field on Hall effect plates that are situated on the IC. the Hall effect plates are embedded in the semiconductor. So as a magnet comes into closer proximity of the sensing IC or is removed out of the field of detection, we can remove this presence or the absence of a magnet. In order to have accurate sensing, the sensing IC and the magnet needs to be designed in close proximity to each other. The Hall effect sensing allows for the inductive sensing, allows for similar applications where we can detect the absence or the presence of any metallic object. This metallic object can be part of the stainless steel or the metal housing. You can laser deposit some kind of conductive material in a targeted area. You can even use a piece of copper foil. How do we detect this? By the disturbance of an inductive field around an inductor. This inductor that I'm speaking about can be a trace on your PCB, a simple coil, 4 or 5 windings of a copper trace on the PCB can realize an inductor, or otherwise you can utilize a surface mount inductor. In this instance, the sensing circuit and the sensing IC do not need to be in the same location. We can have the sensing IC that is driving the inductor in a remote location. So let's take the example of the cartridge detect in the coffee machine. You can have your sensing IC up towards the user interface area, and just by routing 2 traces, either on a flex, or they can be 2 wires, or they can be on the PCB, 2 traces run down to an area where we can detect the cartridge is being put in and out. So this also allows to do multiple channels of inductive sensing. You can have a single IC that is detecting 3 or 4 different inductive sensing channels because you have the advantage that the IC do not need to be in the same location as the sensing activity. So the sensing parts distributed throughout the machine, all controlled by a central IC. So talking about the inductive sensing, I just said that we measure the disturbance of an inductive field around the inductor. This disturbance can happen through any non-conductive material. So in the next instance, and maybe an exploded view explains this better. If we look at the conventional snap dome that all engineers would be familiar with, a snap dome relies on the premise that we need to complete an electrical circuit. When the snap dome collapses under pressure, it will complete an electrical circuit, and the current can flow. The current can flow from one point to another point. What AZOTEQ is proposing here is to have the inductive sensing circuit sealed inside the appliance. So on the opposite side of the barrier, and when I say the barrier, I mean the housing, on the opposite side of the housing, on the inside, we have an inductive coil. We excite the inductive coil from the IC, or the IC drives it, in other words, and we generate some kind of inductive field around this inductor. We have a metal snap dome on the opposite side of the barrier. So no physical contact, no electrical contact, mere snap dome on the opposite side of the barrier. When this snap dome collapses under a force, like you would press down on any tactile switch on any snap dome, this change in the location of the metal causes enough disturbance in the inductive field on the other side of the barrier that we can measure it. So what this means is From the user perspective, you generate the same tactile sensation and tactile feeling as pressing down on a snap dome. But from an electrical perspective, you do not need any galvanic connection between the sensing circuit and the moving part. Now, this all of a sudden opens up a lot of possibilities. First and foremost, reliability. When we have an appliance that is exposed to water, there's always the risk of water getting into your electronics. There's the risk of corrosion. There's the risk of dust and dirt and grime, especially in the kitchen, for grime to settle in between the moving part and the electronic. So what I have on the screen here is a very elegant solution to make a fully waterproof enclosure. All the electronics are hermetically sealed inside the housing. Your moving part can now be exposed to water or grime or dirt or whatever the case may be, because such water or grime cannot interfere with any electrical connection that traditional sensing techniques are reliant on. I hope this point is clear. It is something new, it is something novel, but it certainly holds a lot of promise in all kinds of kitchen appliances. Any kind of user interface that is exposed to water can be significantly simplified with this technique. At the end, we'll allow some time if there's more questions about the specific application. So if we can have a button that measures the instantaneous change or collapse of the button, surely we can measure multiple locations of such a button. In inductive language, we talk about this moving part as the target. You can now imagine if we put down multiple coils and we move a target in the vicinity of these coils, that we can reliably detect the location of the target material without needing any electrical or physical contact between the moving part and the sensing electronics. So this, an expansion of the button. The button would be a one-dimensional case, and now we are proposing a slider, which is a two-dimensional case to measure some kind of input. Such a slider would typically be used for speed control or temperature control in kitchen appliances. If we look at an animation of how such electronics would look, on my screen we are proposing 6 coils located adjacently to each other on the PCB. The number of coil and size of coil will determine the accuracy and the resolution that you achieve. If you simply need 5 or 6 positions from the slider, we can get away with a lot less coils. This animation was extracted from an appliance where we needed a very high resolution of up to 0.1 millimeter of accuracy. All right. So what we are showing on the screen here is a typical PCB. 6 coils are driven by or excited by the AZOTEQ inductive sensing IC. We drive these 6 coils, we excite an inductive field, and then as a metal target disturbs these coils or disturbs a coil partially, we calculate the amount of interference and we report a linear position of the slider. We can report to the master controller. So this means everything that you see on the screen in green can be behind a solid barrier, and the moving part is on the opposite side. Absolutely no electrical connection required. You simply need to I have some mechanical guide for your slider, but no electrical connection down to the electronics. So this all of a sudden opens up applications like the ones that I showed before, where making a slider with electrical contact is an absolute headache for the electronics designer and for the industrial designer. This AZOTEQ technique simplifies matters greatly. We actually have a demo kit that shows exactly this. If there's some of our audience that would be interested in such an application, we are happy to supply you one of these demo kits. I'm not sure how well my camera's lighting is. It's not easy to see the coils inside, but the principle is clearly displayed on this demo kit, how such a contactless slider can work. I think this particular one reports 1 millimeter of accuracy. So as I move my slider along, we can see the location of the slider reported on the main screen. I said before, the IC can drive or excite multiple channels, so we can even combine sliders and buttons into a single user interface. Our ICs, all of them, support Hall effect sensing as well. So if you have another secondary input, the example on the screen here is that of a trigger that needs to be pressed down with your index finger. So in the instance that we have on the screen here, the trigger can be sensed by a Hall effect IC, and the user interface can be performed with the inductive sensing technique. Another interesting and important user interface is that of force sensing. Now, whereas before, when we were looking at the snap dome, we sensed the instantaneous collapse of the snap dome. But we are not only reliant on a large change of inductance, it can be a linear move or a linear change as well. So let's say we have our coil stationary and we can control carefully how much a target material is moving closer and further away from the coil. Then we can perform some kind of force sensing. If the housing is stiff enough to give some kind of resistance to the push or the press, the housing will return to its original position after the force is applied. But we can reliably detect changes as small as 2 micron between the coil and the target. Now, this force sensing again opens up a new ways for not only the user interface but simplifying the design from a manufacturing perspective, from a reliability perspective, but also from a aesthetics perspective. We can now make beautiful and seamless outer shells because we are not reliant on an aperture and a silicone membrane anymore. You can have a completely smooth, completely seamless outer shell and have a force sensing or a grip detection as your user interface. On the screen, again, 2 graphics to help our user understand how such a construction would be implemented. On the left-hand side, and I hope my laser pointer is clear, On the left-hand side, we are proposing a concept for the sensing circuit as well as the assembly of such a sensing circuit. If you consider the brown part to be a flexible circuit, in this instance, we will have the inductive coil, will be a trace on the flexible circuit. We are folding back the flexible circuit to hover over the coil. The top part of the flexible circuit would have a large copper pore, which would serve the purpose of the target. And we keep it in position with a sponge-like material or a compressible material. So the unit is pre-assembled like this. And then it can slide into the appliance into position. The sponge makes sure that the target is preloaded and securely pushing against the outer shell. And now, as the user will squeeze on the outer shell, the target material will move a few micron closer to the target, and we can detect that deflection. In another embodiment, if you do not have enough space on your PCB for a trace to realize an inductor, you can also make use of a surface mount inductor. This is typically where space is at a premium. The surface mount inductor serves the purpose of the coil exciting the inductor field. And in this instance, we are using some kind of spring pogo pin that is preloaded. The spring tension is pushing it against the inside of the outer shell. Then as a user applies force to the outer shell, this small flange of the pogo pin will move closer to the inductor, and we can measure that change in distance between the flange and the inductor. So force sensing, if it is a user interface that users find practical, this can be a very elegant way to make a beautiful industrial design without needing to ruin your industrial design with holes and with buttons. I use the term the force sensing should be acceptable to users or the user experience. Typical cases that work well is where the user is used to gripping something. A blender, you will typically grip your blender to start mixing. If it is a pinching function for users, then the force sensing is an applicable user interface. Cases where it's not convenient, if you have an appliance, let's say a home entertainment appliance, or you have a set-top box that is freely standing on your table, in those instances, applying a positive force to the user interface will just push your appliance off the shelf. So in those instances, the force sensing doesn't make sense. But where the grip or the interaction of the user with the appliance is such that it is easy to exert a force, or even it is natural to exert a force, then this becomes a very practical user interface. So an extension of the force sensing would be to detect a larger linear movement by an inductive sensing technique. So before we said, with the force sensing, we will squeeze the housing and we can measure deflections as small as 2 microns and report an interaction based on that. But there's other instances where we want a longer travel for some kind of user interface, or typically this would be motor control. If you are playing a game with your console, you want speed control on a trigger. If you have something like a blender or a mixer, you want some kind of speed control that is performed by a trigger action. The trigger button is based on the concepts that I already explained thus far. My animation on the screen is that of a trigger button typical in gaming console controllers, but the principle is exactly the same for a home appliance, something like a blender that requires speed control. We will have an inductive sensing coil on the stationary part. Your target will be on the moving part, and as you squeeze the trigger and the target moves closer to the coil, we can interpret the distance. Although we do not know the exact distance, we can measure this change in distance between the coil and the target, and that can be translated to some kind of speed for the motor control. I mentioned that we do not know the exact position. In these instances, typically we will calibrate the device once at production, so we will have the two extremes at the maximum deviation and at the minimum deviation, and that total excursion will be mapped into 8 or 16 positions or whatever the case may be. I think I don't need to say it again, but the trigger, again, a fully waterproof solution where the electronics can be hermetically sealed from the moving part. All right, next up, another variation of contactless sensing. You see the golden thread throughout this whole presentation is the fact that we can seal moving parts from the electronics. It means we can have a solid barrier between moving parts. And once you have a solid barrier, you introduce reliability, you simplify mechanical construction. So the next proposition is that of a rotational kind of input. Many appliances in the kitchen has a rotational input. If you think about your dishwasher, if you think about your washing machine, a stove remains a very nice user experience if you can adjust the temperature with some kind of rotation input. So what AZOTEQ is proposing here is once again a contactless input method. On the left-hand side of the screen, we are depicting a sample of such an implementation. In this instance, we have 6 coils, and the rotating part has 6 targets. Now, as these targets are swept across the coils, we can interpret the rotational position of the knob. The graphic that we had before allows for a completely seamless outer shell, but in the instance where you need to locate the knob in an exact location, you can use a strong magnet to position it at the exact location over the sensing circuit. But you can also make the magnet weak enough such that you can remove the knob, clean the surface, even remove the knob for a safety feature if you do not want your kids to play with the stove. But those are convenient features. Again, the key advantage that this contactless technique brings means that now you can have the front of your dishwasher can be a sealed surface. You have your sensing electronics behind the sealed surface, and you have your knob, the rotating part on the inside. Any water that runs down the knob has no effect on your sensing electronics. Ladies and gentlemen, that is my story, or my formal story at least. You have the option to pose some questions. We still have a little bit of time left until we get to the end of the hour, so I'm happy to take a few questions. If I cannot answer the question here in the call, we are happy to come back to you afterwards.